Hi, so in this video we're going to be looking at we're going to be looking at exercise 11i, and it's using something that's new to you called the trapezium rule. Whilst you may have never heard of the trapezium rule before, it really is just something you've covered in GCSE and just giving it a formula in order for you to estimate areas on the curves. And if you remember back to GCSE, you had to work out areas under curves by using trapeziums, and you'd work out the area of these trapeziums, and then you'd add them together, and then you'd work out the area underneath the curve as an estimate. And that's essentially all we're going to be doing today, except we're just going to create a formula for it, which is in your formula booklet, and just highlight a few key words which you need to be aware of. So just running through this first of all, it says in year 11 we were sometimes asked to estimate the area under a curve. This is necessary in year 13 as we cannot always integrate a function. So there are some functions which we will not be able to integrate, and you'll be asked to work out an area, or rather you'll be asked to find an estimate of the area, in which case you will use this process. So to find the precise area under it. So in year 13 we meet a more formal formula to do this, and if we consider this graph here, we'll just run through how this kind of works. So we assume the area has been split up into some strips, let's say into n number of strips. So strip 1, 2, 3, there'll be loads more in between there, and then the last one will be the nth strip. Each of those strips needs to be of equal width. I know this isn't of equal width, that's just meant to highlight there'll be strips in between there. So of equal width in order for this to work. And whilst we have n number of strips, what you'll see is that we have something called ordinates. So for example, if we look between here and here, we have 3 strips, but that means we have 1, 2, 3, 4 ordinates. So whilst we have 3 strips of equal width, we have 4 ordinates. And it ends up being that the number of ordinates is always 1 more than the number of strips that you have. So if we have n number of strips, then that means we will have n plus 1 ordinates. And just to re-highlight, the ordinates are these lines here. Okay, and each strip is approximately a trapezium. Hence why this will be called the trapezium rule. So how do we work out the total area underneath the curve? Well, what we need to remember is that each of these are trapeziums, and they are of equal width. So they all have that same height. And if you were to turn these trapeziums sideways, you could call that the height. Okay, so those are all heights. How do you work out the height of each of those trapeziums? Well, if that there is B and that there is A, and you have an n number of strips, then the height of each of those trapeziums is going to be B minus A divided by n. So that's the height of each trapezium. And how do you work out the area of a trapezium? Well, it's half the sum of the parallel sides and then times the distance between them. So if we look at trapezium number 1, the area of that one, but before I go on, actually I should probably label a few things. So if I just zoom in for a second, if I label this ordinate y0, the length of this ordinate, y1. So these are just the heights between the x-axis to the curve. And I'm sure you can appreciate that's just the y coordinate for each one. This one here would be y to yn, and then this one here is the one before, so it'd be that. So moving forward, if we want to work out an estimate of the area underneath the curve, then the area is going to be the sum of each trapezium. So if I look at the first trapezium, half the sum of the parallel sides, so that's going to be y0 plus y1, those are the parallel sides. It's going to be half the sum of the parallel sides, and then times the distance between them. So half the sum of those parallel sides, and then times the distance between them, which is of course h. So that's the first one. Moving along to the next trapezium, half the sum of the parallel sides, so half the sum of the parallel sides of y1 and y2, then times the distance between them. And then the next one, half the sum of the parallel sides times distance between them, and then you would carry on all the way to the last strip, and the last strip, and we can use this from our diagram, would be half the sum of the parallel sides and then times the distance between them. So we end up with an expression that looks like that, or rather the beginning of the formula that looks like that. Each one of those terms has common factors. We have a half in each term, we have an h in each term, so I'll take those out, factorize them out. So we have half h, and then you have just y0 plus y1, and then if you can continue, you end up just having them a y1 with a y2 plus a y2 plus a y3 plus all the way to the end and so we end up with that. Now it's not, I mean, you can tidy this up some more, which we will. If you look inside the brackets, almost everyone, look, that y1 appears twice, the y2 appears twice, the y3 again will appear twice, and the reason they appear twice is because this y1 here, for example, is the length for trapezium 1 and trapezium 2, so it needs to be used in both calculations. This y2 here, that length there, that ordinate, is used for trapezium 2 and used for trapezium 3, so it's going to be used twice. So all the ordinates are used twice except for y0 and that last ordinate. And so we always have two lots of every ordinate. So here we had two lots of the y1, two lots of the y2, and we would have two lots of the y3. So to simplify what's inside the bracket, we can write instead, it's definitely only one of these, and it's definitely only one of these, and then we're adding all the others, but there's two lots of all the others, so it's two lots of y1 plus y2 plus y3 plus all the others as well. And then that's the formula. That is known as the trapezium rule. just to tidy this up ever so slightly, I said area equals. It's not an exact area. It is, of course, an approximation. And you'll find that formula in your formula booklets. Okay, let's apply this to a question then. So here we have just one question we're going to run through. The diagram shows a sketch of the curve y equals sec of x. The finite region R is bounded by the curve, the x-axis, the y-axis, and the line x is equal to a third pi. Question A. Complete the table with 5 ordinates. To enable you to find an estimate for the area, give y values correct to 3 decimal places. So it says to complete it to 5 ordinates. So that means there will be 5 vertical lines, but 4 strips. So it's going to look roughly something like that. 4 strips, but you do end up having your 5 ordinates. Ordinate 1, 2, 3, 4, 5. And we're going to fill this table in, giving our values correct to 3 decimal places. So we know that the curve is y equals sec of x. And we're going to work out, we're going to fill in the table. But in order to fill in the table, we actually need to know where that is, and where that is to substitute in to work out each of these heights. So what we need to remember is that there are 4 equal width strips, and so what we're going to do is we're going to take that distance from between 0 and pi by 3 and divide it by 4 equally, and that will be the height of each of the trapeziums. So the height is going to be equal to pi, the distance between pi by 3 and 0. Now here we don't have to write minus 0, but if you were doing it between something and not 0, you really want to fill that bit in there. And then we're going to divide that by 4 because there's 4 equal strips. And when you do that, you end up with each of these strips having a height, or each of these trapeziums having a height of pi by 12, which means that there is pi by 12. This one here would be 2 pi by 12, which is of course pi by 6. And this here would be 3 pi by 12, which is then of course the same as pi by 4. And so now I can begin to fill in my table. So there we'll have pi by 12, pi by 6, pi by 4, and then we substitute those values into that, making sure I calculate it in radians because this won't work otherwise. So using your calculator, you substitute these in, you work these out, giving each result to 3 decimal places. Right, and then that's filled in. So next, use trapezium rule with all the values of y in the completed table to obtain an estimate for the area of R, giving your answer to 2 decimal places. So we're trying to work out the area of R. So the area of this R is approximately, because remember it's just an approximation, going to be half times the height. The height of each of these trapeziums is pi by 12. It's the first ordinate part plus the last ordinate, first plus the last, plus 2 lots of all the others. and then you can type that into your calculators. And now I'm using an equal sign because over here, that's the area of R is approximately what I've just written over here. But then this calculation does then equal the following line. So you type that into your calculators, you'll end up with 1.34 units squared. And that's it. That's how you use the trapezium rule. It is just a formula that just adds up trapeziums together. The bit where people make mistakes sometimes just working at the height between each trapezium or of each trapezium.